this on the web version of this. And so we are here talking today on our fourth session about advanced statistics for researchers. And we're talking primarily about causal structure. And the title of today's session is Using Structural Equation Modeling to Test the Validity of a Causal Structure. And we are going to do that. But I have to tell you that in preparing this session, this will be the second time I've done this. And I thought the first time, and I think even stronger now, that the real emphasis here is about thinking about causality. And SEM is one of the applications we can use when we're testing it. So it's really big causality, small SEM. And I think it has to be that way. And so that's sort of my focus. The other thing before I even launch into this is that this term advanced, I want to use cautiously because, well, there are some circles where structural equation modeling is and you might even get into factor analysis depending on the class. And the degree that you do that would be up to that particular teacher, but that's about as far as you get. And where that leaves is where structural equation modeling really picks up with confirmatory factor analyses, which we talked about in session 1 and 3. And then you get into some other Let's dig into this. Causality is about design. So if you read any text on structural equation modeling, you will hear conversations about how much causal inference can you get from a structural equation modeling. And there's a whole school of thought that says that when we have those ovals that have the different latent factors in them, and we draw a one-directional arrow, that is automatically a causal inference. And there's another school of thought that says, whoa, hold up now. Causality is a little bit bigger than the statistical technique that you're doing. And in a lot of ways, they're both right and they're both wrong. Okay? So a lot of the people that do the hold up routine are really thinking about causality from the perspective of, I have an intervention, I'm going to go out and see if by doing this I made a difference. And you can do that with structural equation modeling. But that is causality. It's not a different kind of causality here, but it's causal inferences of a different construct. So a lot of times when we're looking at causality in structural equation modeling, we're thinking about how do things fit together and how do they work together. And I'm going to do some examples here in just a few minutes of what that really looks like. But for example, one of my doctoral students right now is working on a study asking, there are these 4 traits that seem to make up teacher professional identity. Do they lead to professional identity, or do they emerge from somebody's sense of professional identity? Which comes first, the chicken or the egg kind of a thing? That's really a question about causality, but it's a rudimentary question about causality. It's not asking, if I go out and do something, will this make a difference on somebody's job satisfaction levels? That's another type of study that is also getting at causality. And so I think the first thing we have to understand is that a lot of times in structural equation modeling, we're dealing with single group designs, and we're going to talk about study designs here in just a couple of minutes. So we're not looking at comparing a treatment versus a control, because we're looking at, in some cases, natural phenomena or naturally occurring phenomena, and we're looking at how do they fit together, and we're really, in some ways, thinking about developing a framework for how do we understand this system to work. Okay, so outside of any statistical considerations, there are 3 primary characteristics that you really have to think about when you're thinking about causality. And I will say that causality is sort of the holy grail of research, right? And it really doesn't seem to matter whether we're thinking about causality for medical experiments or whether we're thinking about social science experiments. We're really thinking about, can I establish that if something is introduced, or if I understand the formation of something, I will understand the outcome, right? So the first thing is that before you can get causality, the two constructs, the two variables, have to be related in some way. So this is where you get that covariation. Remember, covariation is an unstandardized version of correlation. So if you're not sure what covariation means, but you do understand what correlation means, then they really conceptually mean the exact same thing. They're just two different ways of measuring an association, okay? And they are perfectly, those two measures are related because one is just a transformation of the other, okay? So we're really thinking about correlation. If things are not related, they can't be related causally. So in a basic statistics class, you would have heard that when you're doing R, when you're measuring Pearson's R, that you're getting a correlation, and that's not causation. You get all kinds of examples of why that's, of things that are associated but are not necessarily causal. And I've got an example of that, a big one here in just a second. That's great, and it's absolutely essential in those basic classes that you understand correlation. But you have to have correlation if you're going to get causation. It is a necessary, but not even close to sufficient condition for causality, okay? Temporal order. The cause always has to precede the effect, okay? And I think that one of the things that we really think about hard with structural equation model analyses is the temporal order of things. What's the relation? What leads to what, okay? And then if we have something that we think is a causal effect, we have to make any alternative explanations, okay? And the crux of this is, how are you going to know when you've got all of the possible alternative explanations? Well, one way is you've got to have a strong literature review and understand what the current research is. So you've got to know what all the schools of thought are about how the system works to begin with. You've got to understand what the different variables are that could impact it. In other words, you have to have a strong conceptual framework of the phenomenon you're studying. Otherwise, you've got no chance of doing that. Once you have that, then you're going to explain away possible alternative explanations based on your literature review and conceptual framework, with the always caveat that somebody else could come up with something else that we haven't seen yet or we haven't thought about yet that also explains this, okay? But we do eliminate them as best as we can. And at that point, then we might be prepared to say we just might have something causal. Single studies are really hard for establishing causality with any particular strength. Typically, what happens is you've got to have replications and you've got to get similar results over multiple trials before the research community is really going to accept that we found causal inference. Now, if you'll recall, probably about 10 years ago or so, I know my timing isn't right, but when the HPV vaccine first was introduced to the public, and it was one of the big reasons that that made such strong news headlines was because the scientific community was so stunned by the strength of evidence that said, if you take this vaccine, you will not get HPV. They were really, really on the fast track. And I think now they've backed it off to like 99% of the time. And even then, they weren't saying 100% of the time, but some of the stuff that you would hear on NPR at the time was, it seems like we don't have a single case in our sample that was able to get HPV after they got this vaccine. We think we've got really strong causal evidence. Okay, so here's my favorite example, population. So these are actual data. I went back into the Census Bureau and updated from estimates from 10,000 BC all the way up through today, and then with their projections for the next 20 years based on their calculations. There's a world population clock on the Census Bureau's website. So that's kind of fun. You can always get this kind of data. And there is a clear pattern and it's clearly not linear. We're nowhere near the top of wherever this is going yet. We're still climbing. The estimates going up into the 2050s are we're going to hit 9-point-something billion. Remember, this is in millions, so 8,000 would actually be 8 billion. Okay. There are different models for population growth. The one I've got up here that is the best fitting model that I could find was an exponential equation. And the R squared was 0.7855, and our R was about 0.8889. Okay? Which is a pretty strong correlation, and that's a pretty strong predictive quality to that model. How far it extrapolates, we don't know, because there are alternative models. For instance, there are some people that believe that this is the first end of a logistic curve, and that there, as we get higher, it will level off for some reason. They don't think that's going to happen until like we get to like 12 billion, so we've got a ways to go up here before it would start to do that. But we really don't have any data right now at the leveling off. We're not at the leveling off point. So remember that when you create a model for something, extrapolating beyond the range of data gets iffy, because it's only a good extrapolation as long as your model holds. Okay? So that's all about modeling. Why is this here? Why would I put population up in a conversation about causality? We have population regressed on time, basically. And I've got a really strong correlation. Yeah, time didn't cause the population growth. Okay? This is an example of a pure correlation relationship, and there's no way that time caused the population unless there was some sort of if we were looking at, say, anaerobic bacteria that reproduced by fission, asexual reproduction, in which they would just do this based on, as time progresses, they're just going to split, cells are going to break down or something. But I can't even think of a good example where that would be causal, because even then there would be things that happened over the time that led to that. And so if we wanted to think about this in another direction, thinking about life expectancies. At one time, you would have thought that with the strong correlation between time and age and life expectancy, that our life expectancy was about 45 to 50 years. And that's just the way it is. And if it was causal, then there's really very little we can do about that. Except that now we have a life expectancy of somewhere between 75 and 80 years. And progressives estimate that at some point we're going to have a life expectancy in our time span, in our lifetime, we're going to be seeing people living to 100+ years regularly. Like people live to 80 today. It's not, it's amazing and it's a long life, but it's not particularly rare to see somebody that's 82 years old now. They're saying that within the next 50 years, seeing people that are 100 years old will be about that common. Okay, so we're expanding that, which again suggests that time is not the causal variable, right? There's got to be other things coming in. Okay, so now we're to research design. If you're going to establish causality, your design is going to be absolutely paramount to everything that you can do with the data once you get it. I thought this was a pretty good picture because this is where you might completely destroy any chance of causality if you don't attend to things properly. So you have a handout. They may be front and back of one sheet. That on one side you've got research designs, and the other side you have threats to validity. And I want to talk about the research designs first. This. All right, so I used a framework for thinking about research design. This came from Shadish, Cook, and Campbell's Quasi-Experimental Designs textbook. So they have some one-group only designs. So you've got things, just in terms of reading this, you've got one group post-test only design. So you've got some sort of a treatment, and then you've got an outcome measure. Okay? This is, again, not my notation. This is Shadish, Cook, and Campbell. At the bottom of this, you'll notice that there are some symbols here. So an O is an outcome measure, and X is a treatment. NR is a non-random group assignment, and R is a random group assignment. Okay. So then going back up to the top, you will notice that all of the designs that Shadish, Cook, and Campbell put in here have an X with them. But if I was actually just going out and trying to understand a psychological phenomenon, for example, like attitudes, satisfaction, motivation, things like that, I might not actually have an X here at all. It might just be a one group single measure design because it's not a post test because there was no intervention to happen before that. Most of the time in research, when we're dealing with causality, we usually have some kind of a treatment that we're saying this measures it. But in structural equation modeling, there may not be an X because we may only be looking at the relationships among various factors. Okay. Notice some of these will have some dots in there where you can act, like for the longitudinal stuff, you might have more than one outcome, you might have more than 5 outcomes. How many outcome measures you have depends on the design of what you're particularly studying. So these are flexible notations, but these are sort of how they present them. So you can have pre-test, post-test, a non-equivalent post-test. So for example, I might have a pre-test that isn't like the post-test at all. So then I'm not going to be able to just do like mean differences or not directly anyway. You might have a couple of different outcome measures before you ever introduce a treatment. And then you might look and see what happened at time point 3. There could be the same amount of time between O1 and O2. So you actually get a sense of what is a natural level of growth for this group. And then you have your intervention, and then you have a third measure. All of these designs, in general, are considered weaker for making causal inferences, the one group only designs, simply because you have some threats to validity that make it hard to establish causality. That doesn't mean it's impossible. It means these are tougher to do it with. And it would have to be, you have to be really careful about inferences that you're making with these kinds of groups. The next set are quasi-experimental designs. You'll notice that all of these start with an NR. They're quasi-experimental because they're non-random. So when Shadish, Cook, and Campbell talk about non-random, they mean group assignment, not sampling. So sampling is different from group assignment. So I might have in my studies I do math education, so I might have a group of high school math students. Well, they weren't randomly assigned to their classes. They weren't randomly selected to be in the classes that I'm studying. They were put there purposefully because of their grade level, how they performed in previous math classes, and sometimes alphabetically, okay? But it's done for non-research purposes, the way that they get assigned there, so that it's not likely to include a lot of bias, but it's not a random sample. One of the ways that I can mitigate some of the effect of that is to have multiple classes and to do some sort of a non-random assignment of class, or I can do a randomization of classes to the group, so then it doesn't matter which class I have. But typically, if you have a non-random sample or a weighted sample that's not particularly representative of your population of interest, then you need some sort of a way to equate groups that you're comparing. If you do non-random assignment, you have a little bit longer of a road to plow for that. So you've got to actually make an outline and say, here are the possible characteristics that they might be different on that could impact the results of the study, and here's how equal they are. One of the ways that we do this is with pretests. So this one right here, I think it was bold on your all's. I think I bolded this one, or it might be the one down below that's randomized. This one is sort of the quasi-experimental version of the gold standard design that RCT, where you have a pretest for a treatment and a control group, and then the treatment and control get their whatever they get, and then you get a post-test. So then the pretest is one of those ways that you can say, okay, so regardless of the differences that they have on anything else, before we started the study, they were equal on these measures. And then from there, you're looking at growth to O2. So now you're looking at a slope rather than a point estimate, right? Okay, so then there are some pretty robust quasi-experimental designs. For instance, this untreated control of the switching replication. I actually accidentally fell into doing this one time because I had teachers that were going to be doing control classes, but then they wanted, everybody needed to get the units that was going to be the treatment unit at some point. And so what we did was that we did basically this design right there. And then the control group got the treatment after we were done with O2. So then we were able to actually see, well, okay, so at that point, how well would the O2 scores here stay stable without the treatment? If they went back down, went up, that would be stronger than what it said that treatment was doing has some sort of a causal impact on the system. Another design is where you have a reverse treatment control, where you can add a treatment to one and take that same treatment away from others. Maybe you can see the director there. You have to ensure that you have a right to something taken away from things when you're considering design. You've got cohort controls with pretest. You've got a cohort design where you've got one cohort doing one thing and another cohort doing another. So in other words, here's one cohort, and those three, you've got their outcome measure. Then the next year, you do something for the next cohort and you compare cohorts. Not a particularly strong design for some things, but if it is a design that you can use if you're dealing in a system that has groups of people that are going through a system together. Okay. And then we get to the preferred ones. I actually left off a quasi-experimental design I'm going to come back to in a second that isn't part of this list. But that's because it's not a comprehensive framework, it's a set of designs. So in a lot of ways, the randomized designs are very much like the quasi-experimental designs, except that instead of having an NR here, they have an R, because they actually did get randomly assigned to groups. Once you have randomization, it eliminates a lot of problems for you about equivalence, because any differences in the groups can't be because of the assignment protocol, because there wasn't one, it was just random. Common misconception about random assignment. Random assignment does not mean that you have equal groups. It means that any differences in the groups are not because of the assignment process, or that they're not based on anything that it wasn't a bias that was introduced into it. It's just random chance, okay? And if we actually run series of randomized trials, you'll see that they don't come out systematic. They don't come out necessarily equivalent. You got a random sample. So this is just a random sample. Sometimes it takes more than one to really get a complete picture of what's going on in the population. Depends on your sample sizes. Obviously, the bigger sample, the more likely you are to be representative of the population. All other things being equal. The one that I had bold down here, this is what is often considered the gold standard. That randomized trial with a pretest and a control group. It's considered by some people. Quasi-experiment doesn't have one of these. It's called a regression discontinuity design. Regression discontinuity basically says that you take the pretest. It's basically wrapped up inside of the NRs. You take the pretest, and there's this cutoff score. And anybody that scores below the cutoff gets the treatment, and anybody that scores above the cutoff doesn't get the treatment. And then when you get the post-test, you look at the change of slopes at that point, at that cutoff point, to see if there's a difference. And it basically lets you target groups with the highest need while still being able to make pretty strong inferential claims. Okay? So that's research design in a nutshell. That I basically just summarize an entire course in 5 minutes or less. But the
the reference for this book is at the bottom of that handout. This is a book that I strongly recommend that anybody that's serious about doing research gets a copy and puts it on your shelf. Read it, read the first 4 chapters before you ever do a study, and go back to it every single time you start to design a new study. This book has actually been out in one form or another since the 1960s. Before Shadish got on there, Campbell and Stanley, and then it's Cook and Campbell, and now it's Shadish, Cook and Campbell. So we're pretty far along on the editions. It's been around for a long time. It's a notation that everybody knows, and using that as a framework for thinking about study design will help you as you're thinking about making the strongest inferences possible. On the other side of that handout are threats to validity. And these come from that Shadish, Cook, and Campbell book also. They basically define 4 different types of validity that you can have threatened. You have internal validity, which are reasons why the relationship between 2 variables might not be causal. In other words, so this is a threat. So threats to internal validity are reasons why causal inference may be incorrect. Okay? So a couple of things here. Selection bias is probably one of the ones that we see the most. Okay? You've got 2 groups, you compared them, but the treatment group was stronger to begin with on those measures than the control group, and so of course they ended better because they started better. When you have non-random assignment of groups, this is a really big deal, and you're really making the case that that didn't happen. Okay? You all see it on political polls all the time during the election, right? 25 out of 25 Democrats said that the Democratic candidate should be elected and it would be the best choice for our country. And 24 out of 25 Democrats said that while we have a Democratic president, our country's going the right direction. And lo and behold, 24 out of 25 Republicans said we're going the wrong direction. I think we got a selection bias here, right? Going to the independents doesn't necessarily fix a selection bias, right? That just says there's a third group that has a different opinion than necessarily the other 2 that might be a mixture. Okay. The first one, ambiguous temporal precedence, that's when the cause sometimes doesn't happen before the effect. Okay. There's some other things here. The next one I really want to focus on here is attrition. When you lose respondents for some reason, you have to consider why you lost them, because it could very well be that if you see a causal effect in your outcome, but you lost a lot of subjects in your study, it could be that the people that you lost, if they had stayed in it, would have meant that you didn't get those results. In other words, there might be something fundamentally different about the levers that you need to consider. I'm going to show you a chart here in just a minute that the What Works Clearinghouse uses to decide whether causal inferences are warranted from a study. And of all of these different threats, you start off with selection and you go straight to attrition. Okay? And that's why, is because most studies have some level of attrition. And so commonly you're going to see that you've got to make sure that the people that left didn't impact your results in some way. It's difficult to do that. So you have to think about attrition in your study design, and what are you going to do when people want to leave, and how are you going to manage that and its influence on the results. Okay? I can actually use particular instruments that would actually impact the result. There was a study that came out a couple of years ago that was talking about education research, and they were basically saying that when studies would, if you took 2 different studies of the same intervention, and you put them in basically the same types of populations, and you did the same kinds of things, and you had the same quality teachers, and everything else is basically equal. But in one of those versions, I measure with a teacher-made instrument. You just do a classroom test. And the other, I do a standardized test that's gone through all kinds of reliability and validity checks. 9 times out of 10, you will get weaker results with the standardized, stronger test. In other words, that teacher-made test has some bias introduced into it that actually favors the treatment group, which sort of makes sense. If I'm in an education setting, the teacher is writing the test to a unit that he or she taught, then it's likely that those test items are going to be related to the exact treatment that they got, which would possibly give the control group an unfair disadvantage. So you have to think about the instrumentation when you're thinking about what kinds of inferences am I really trying to make. This regression up here, this is not about linear regressions per se. This is not about the regression analytic technique. This is that if you chose people with extreme scores on one variable, so in other words, if I did like a regression discontinuity, I chose people that had low scores on something. Just because they have those extreme scores there doesn't necessarily mean that they will have the same extreme scores on other variables. So when I measure those other variables as an outcome measure, then I very well could confuse the effects with a treatment effect. Here's a good example. Special education populations. Okay? They may have extremely low scores on something, and then they might actually turn around and be very good at a particular subject that you're testing. Okay? They might have very high social skills. Could happen. I actually taught a class one time that was 32 students, 28 of them were special education, and it was one of the strongest classes I had all year. It was an Algebra 2 class. And so the notion that just because you're special education means that you may need more, that you're at risk for a particular subject, doesn't necessarily hold, and that's what this is talking about. There's also another thing wrapped up in this called regression to the mean, that as you get more and more scores, things will start to look more like the average, the population average, and so you start getting less variance in the system. If I do testing over and over again, if I use the same test repeatedly, kids will get better at that test regardless of whether they actually know what's going on better or not. And so there's that testing effect. When I was in grade school, we had to take the California test of basic skills, and there was a memory portion to that. And every year it was the exact same vocabulary words. And so even to this day, more than 30 years later, I can still say a Baloo is a bear. A Yonker is a young man. But that doesn't necessarily mean that I have a rich vocabulary. Okay? Threats to internal validity are probably the most pertinent to what we're talking about today, because that's about things that would keep you from being able to make causal inferences. And so when you're thinking about trying to establish causality to any degree, go to this list first, but not by itself. When you start running stats on things, you have to start thinking about the validity of your conclusions based on those statistics. And so you start thinking about things like low statistical power. If I didn't get an effect, did I have a big enough sample size that I could have detected the effect even if it was there? Which can be a problem. Let's see, you got violated assumptions is probably the biggest one. You know, things like normality, multivariate normality, homogeneity of variance across the groups ahead of time. Unreliability of measures is a big one in some fields. Depends on what field you're in. In education, it can be quite a problem because the main statistic we'll use to establish reliability is a Cronbach alpha, which is perfectly correlated to sample size and number of items. And so there's some issues there. And there's some ways to deal with it. All of these, there are ways to deal with them. And again, I'm truncating another half of a course in 5 minutes. But if, for example, you have low statistical power, but you do find a treatment effect, well, then it might have even been a stronger effect than what you found, right? So then when you're writing this up and you say, we actually had low statistical power, which means that the fact that we found anything is amazing, and it could mean that it's even stronger in the population than what we detected in our sample, okay? Violated assumptions, depending on which assumption gets violated, it can have different effects on how the stats are influenced and how many of them are violated. You know, there are several tests that are quite robust to non-normality. Hard to get around the independence of variables issues too much because that affects your actual standard error values, and so you really got to think about the degrees of freedom that you really have. Okay. If I'm looking then at threats to construct validity, these can get wrapped up in internal validity quite a bit, but in a different way. In internal validity, we're basically saying that our inference isn't warranted. Here, we're saying whatever inference you just made, it wasn't about what you thought you were making it about. Okay? So, construct confounding. So, inadequate explication of constructs. There's nothing written back there because all I could have written behind that bold print was the constructs are not explained adequately, which is kind of what it says. And so that's really what it is. I mean, basically, we don't really know what these constructs are. And you're sitting there probably thinking, well, that can't happen. Just, if you're writing a paper, you're going to describe those fully. It doesn't happen that way. What actually happens is a lot of times you read papers that the conceptual framework isn't particularly strong. And so we don't really know how these things fit together, and we don't necessarily know what the results really mean, if anything. Construct confounding. I can have multiple constructs happening at the same time in a complex system, teasing them apart and making sure that I know that the inference I'm making is actually about the construct I mean to be making it about, is sometimes awkward, difficult, and there's a whole host of things that can happen here. For example, experimenter expectancies. I was listening to a research talk the other day by someone that was really concerned about this issue that she grew up as a child in the military, and she was studying military children, so she had a lot of strong beliefs about how certain things should work and do work with those populations. So she was very concerned about her biases coming into play in how she designed the study. But then when we got to the results, and here's your trade-off, her hypotheses, she proved wrong. Well, that's a pretty strong indication that her expectancies didn't bias the results, okay? If she had gotten what she expected to get, then she probably did need to go back and say, based on that and our concern about this issue, we went back and reevaluated every step of the way to see where those biases might have inserted themselves, and we found blah, blah, blah. Okay, there's all kinds of different things that can happen here, like this one's particularly colorful, resentful demoralization. If you've got two groups and one of them is getting the less desirable treatment, they can get upset with you, and their being upset can change the way that they respond. The last type of threat that Shaddis, Cook, and Campbell talk about are threats to external validity. And these are reasons why we might not be able to generalize to the population. So clearly, if I have a construct confound, I'm not generalizing anything because I don't know anything. If I don't have a causal inference as an internal validity, then I'm not going to generalize it to the population. And so there's sort of a good reason for listing this last, because it's the last thing that you would do with an inference, right? You have to get it. You have to get the inference first, and then you're going to generalize it. But even once you've got a strong, valid inference about something, if you use a particular kind of unit in your sample, for example, I'm dealing with special education children in 9th grade. If I dealt with non-special education children in 11th grade, I might not find the same thing. So typically, when we are generalizing about an inference, we want to make statements about what we know. So we know that we included these groups in our study, so we believe that this inference is probably valid for those groups. There's another group that we didn't include that was very similar to one of our groups, so we believe it might generalize to that group also. Or there was no reason to think that our sample was any different than the larger population of high school students, so we think that this can generalize to all high school students. Okay? If I did the treatment a different way, I might get a different result. And so one of the things that happens in a research line, you start off with identifying the variables of interest that you can actually make a difference on. Then you develop an intervention. Then you try it at different small scales, controlled trials, smaller sample sizes, with lots of researcher support, and then at some point, if you've got the results to indicate so, you would go out and you would actually try to conduct a study at a larger scale with less researcher support, in which case this treatment variations thing is going to become a big deal. There was a study about 5 or 6 different education interventions about 20 years ago. One of them was Success for All, might be if you're familiar with some of those things, that's a package that a lot of people know. So that's the caliber of things we're talking about. They studied these places for 5 years that were implementing these different interventions. And basically in year 1, you got the learning curve. Year 2, you had the best implementation across all of these different schools. Year 3, you started having teacher turnover, people coming in, the training not really being there, the excitement sort of wearing off. And by years 4 and 5, you were lucky if you still had people in the building that even remembered it, okay? What they found, though, was that it didn't seem to matter which intervention package they used. It was the same curve every single time. And so their conclusion in this paper was, it doesn't really seem to matter what the it is. What seems to matter is that if we have it, we do it. Well, that's really a statement about treatment variations, okay? It really wasn't about the different treatments. It was about variation in how we implement the treatment. Okay, if I used a different measure, so I did a study once that used 17 mathematics test items. If I used a different 17, I might have gotten different outcomes, okay? And if I had used different students, if I'd been at different schools, I might have gotten different outcomes. Okay, and then the 5th one is sort of a catch-all that if my context is different, then it might not generalize, whatever that context happens to be. So, notice that at this point, we're pretty far into this whole thinking about causality, and I haven't talked about a single structural equation model yet. Okay? Because one of the things that I think is really important for people that are thinking about going beyond a multivariate level, and really it's important at the basic levels also, the stats are sort of the last piece of it, right? That design really, it's sort of like prepping a house to paint. You've got to go through and you've got to spackle all the walls, you've got to smooth everything out, sand things down, plug holes, repair rotted wood, and then when you get all that done, you got the drop cloth laid, you got it taped down, you're all set to go. Then you slap the paint on the wall, and that's like the easiest piece of the whole thing, okay? In a lot of ways, running statistics is like painting the walls, and your design is very much like all the prep work, okay? Let's get past that and go here. I thought I took that slide out, actually. So, yeah, let me go back to that. So one of the things that I'm not going to take the time for right now, because we've got people on the webinar also, but there are 3 questions that I've put here that I think every person that's in this room should think about for the studies that you're doing. One is, are there causal relationships that you're thinking about trying to establish in your studies? How many of you are in the room here are thinking about dissertation or doing dissertation research? And then just other research work in a lab? So most people are thinking about their dissertations. This is going to be a really big thing. Establish that conceptual framework early and get it as strong as you can. One of the big jokes I still have with my mentor for my dissertation was the number of iterations that the conceptual framework went through. Before I even got to proposal, I think we were at like the 80th or 90th revision, because we're like, well, does it really do that? No, let's do that. Well, that doesn't really represent the relationship that we're trying to say. Well, what does it mean to have that arrow there? That kind of thing. And we actually just finished a follow-up study for that, and we were laughing that 5-6 years later, we almost know what that dissertation meant. Okay, but as it may, then you want to think about the design. What kind of a design are you using? One of my biggest pet peeves is when people come to me and they say, I'm going to study whatever, and I'm a qualitative researcher, so I'm going to examine it qualitatively. And to be honest, it irritates me just as much if they say, I love stats, so I'm going to do a ANOVA. Well, maybe you will. I don't know that. First off, what are your questions? What's the design that you're going to set up, and why would you choose that particular analytic technique?
and you might end up finding that you need a mix. Most of the questions that I've seen require, of any level of complexity, require some sort of mixed methodology where you're looking qualitatively at trends and depth of richness of what's really going on, and then you've got the stats to corroborate that, and they sort of feed back and forth on each other that says, here's what we saw in the numbers, and here's what we saw observationally, or however you were doing this, and they jive. And then you need to think about the threats to validity. That's a long list I just gave you. You cannot deal with all of them, okay? Most of them you probably won't have to deal with. What you want to think about is which ones of these are going to have the biggest impact on my study. Is it selection bias? Is that where I've really got to focus my attention for internal validity? Or am I worried that the cause can sometimes happen after the effect? Ambiguous temporal precedence. Do I think I've got maturation issues? If I'm going to study people for a period of time, especially if I'm looking at small children and some sort of a psychological aspect, there's a lot of development happening at those ages, and it'd be very easy to confuse natural growth at that age with psychological development. And they're not the same thing, so you might have to think about that depending on what you're doing. But if I'm dealing with high school math students, maturation is probably not the threat I need to worry about, okay? Because they've already been through some of those early stages of development. They've already sort of established where they are in middle school with math, and that doesn't mean that they're not doing lots of growth. And if I were studying other things about high school students, I might have to worry a lot about maturation. But for math, the research basically suggests that fourth grade, fifth grade, and then 7th and 8th grade are the two big jumps and hurdles that students have to get with math. So by the time they get to high school, whatever that maturation effect was, probably would have already happened. So it's not going to be the first thing that I list in my paper, okay? Whenever you're dealing with these things, you need to understand that it's always a trade-off. You can't do everything in a study. Nobody expects you to. Well, most people won't expect you to. And even if you try, you're not going to be able to. So understand that when you're doing these things, there's a trade-off. For example, I might go with a sample that eliminates a little bit of selection bias, but it might be smaller. So now I've got to deal with low statistical power. Trade-off. Which one is going to be more important here? Well, some of that depends on what you're studying. But these questions, I think, you should be asking yourself before you ever even draft an outline of a proposal. Okay? So I told you that I was going to talk to you about show you the What Works Clearinghouse criteria for causal development. They basically study studies, and they say, well, what did they do? And they might even follow up with the authors and ask them questions that weren't clear from what was written in the paper. But they start off with the first question, before they'll ever say that something meets possibly making causal inferences, is the group determined by a random process? And if the answer is no, you notice we skip a whole bunch of stuff and we get down to baseline equivalence. Are the equivalence requirements met? In other words, did they do the work to say that there's a reasonable expectation that my treatment and control actually were equivalent on the variables that mattered in this study? And if the answer is no, then we're done. You shouldn't make causal inferences about this. The best we should say is that there seems to be a relationship between these two things. And we don't really know why that relationship's there, but we think there's a relationship. If the answer is yes, the very next question is what I promised you it was. Sample attrition. How much do we have students or subjects leading the study? In mine, the students are all usually the subjects, but not really. And then you've got 3 different paths, whether you had low, moderate, or high attrition. And let's start with the low, because that's the best case scenario, right? Low to none. Then you've got to think about sample comparability. Notice that we're not setting baseline equivalence here yet, because in a randomized experiment, the two groups may not be equivalent. They might not be comparable simply because of random selection, okay? So at that point then, if there isn't evidence, then, no, there's a query here. They go back and they ask if random assignment is verified.
But even if there is not sample comparability, but there's low attrition, they take it straight down to it meets standards without reservations. If there's moderate, but the answer is no, then you actually have to think about, is there baseline equivalence again? Have they established that somehow? In which case you need a pretest of some kind on the variables that you're thinking about. And if you have high attrition, you might still be able to establish baseline equivalence, but at that point you're really thinking about meeting it with reservations. And with reservations on their criteria means that we think that there probably are some causal inferences that might be warranted, but there might be things that weren't measured that could have impacted the study, and we just don't know because they weren't measured, okay? So it's sort of that, we think it's probably okay, but be careful, okay? That's their framework, and I think that it's probably good to think about that as you're thinking about the design. So now let's move forward into structural equation modeling, because it's sort of its own analytic framework. And if you'll recall, it is a series of regression equations, all analyzed simultaneously. They're all put into basically, each regression equation is an element of a matrix, if you want to simplify it down. And the matrix is analyzed as a whole before you look at the different parts. Remember that the power of structural equation modeling is that if I'm measuring job satisfaction and I take a questionnaire and I pass this out and people give me answers to questions 1 through 11 on job satisfaction, I believe that those questions represent someone's satisfaction with their job in some way. But those 11 questions are just a representation. And if I do a different 11 questions, I might get something different. Depends on how good of a representative set of questions they are. Having said that, I have this latent factor, this thing that I can't really see, my innate sense of job satisfaction. I've got these observed measures out here that they're sort of a proxy for what we think that really looks like, but then I've got these latent factors that I can't measure directly. Structural equation modeling actually accounts for those and actually includes those in the model, and that's really where its power is. So one of the reasons that we might try to establish causality using a structural equation model is that we're trying to figure out the temporal order between latent factors. In other words, does job satisfaction come before motivation, or is it a result of a degree of motivation? Well, job satisfaction and motivation are going to be two latent factors. Can't really measure them directly, but I can take some surveys and get a sense of what you're doing. In structural equation modeling, we actually put the analysis back at the latent estimates as opposed to the observed variable scores. Okay? Just like we can't see the latent factor, we can't see their temporal order. And so structural equation modeling gives us a way to really think about how that works. And it lets us test alternative explanations for variance. So for example, in an example I'm going to show you in a second, I've got 6 different models I tested, and we were thinking about different ways of ordering these things out, and where did that variance really come from. Auxiliary variables are grouping variables such as gender, socioeconomic status, and things that might actually account for differences, and including those can sometimes remove variance from the system and change the way that the different factors work together. And I've put down here, and I'm sure that there are going to be methodologists out there that would just bristle at this statement, that what you get out of this is a necessary, but just like correlation, it's an insufficient condition to fully establish causality. You might need replications, you might need multiple samples, you might need a stronger group design, but if you can't get this, you can't have causality, okay? So I mentioned matrix structures. I'm not going to go through all of this in detail, except that if you're dealing with this, this is actually the original way that mathematically structural equation model structures were set up by Carl Joriskog back in the late 70s. If you ever use the program Lisserl, these are the matrix structures that Lisserl uses. And what you really have then are
a set of matrices for representing the variables that are observed here and here, depending on whether you think they are predictor variables or effect variables. In other words, this would be an outcome and this would be an input. Okay. Up here you have your latent factors that we think are predictors, or that we're setting up as predictors in our model. And you have your latent factors that we're setting up as outcomes. So in other words, in my example before, if I was asking the question, does job satisfaction lead to higher motivation levels? Job satisfaction would be this oval. Motivation would be this oval. The survey questionnaire items that I measure job satisfaction with would be down here. And the survey questionnaire items that I measure motivation with would be here. And just like any regression equation, if I have y equals mx plus b plus error, right? So these are the error terms of those two sets of equations. Remember, we're now talking about regression equations where the variables are matrices, not a single variable, okay? Which allows us to do a lot. So let's say that I have 15 different constructs in a system. The example I'm going to show you here in a second looks at teacher burnout from a study that Barbara Byrne did back in the 90s. If I looked at every one of those equations separately, and then I tried to put all those results together, my inflation of type 1 error is huge, right? But if I do a whole study of the matrices first and say, in this single analysis, there is evidence that within these matrices, there's something worth looking at here, and then I go deeper to find out where, then I've got a more sure defense against that inflation of type 1 error, okay? Very much the same logic as if I do a multivariate analysis of variance, and I look at the ANOVA F test first, and then if I've got significance, then I will look at the individual variables and say, well, which of my 3 dependent variables really seem to have differences? And then, so basically I go from the ANOVA with significance, I go to an ANOVA, or a couple of ANOVAs, and I can do that as a post hoc because I've already established that without inflating type 1 error, there was a difference somewhere. Now I'm just finding out where, okay? Then from the ANOVA, I can do a post hoc with pairwise comparisons on the groups. Basically, structural equation modeling has all of those. It's like ANOVA on steroids in some ways, except that it's the general linear model, but it's matrices, okay? So here is Byrne's burnout model for teachers. And basically, she's got these 3 factors. The dotted circle is just her emphasis saying that these are the 3 factors that we think lead to burnout or that make up burnout. And then there's all these different factors that she hypothesized would lead to different levels of burnout. And so you'll notice that you can label these by their matrix structure where they would go in that SEM model. And it helps you differentiate quickly which are the dependent and independent variables. Self-esteem in this particular model is both a dependent variable on superior support, and it's the predictor of personal accomplishment. So it sort of fills a dual role, but it still is considered a dependent variable. The only independent variables would be the ones out here that there are no arrows pointing to them. So there's nothing in my model that is explaining work overloads behavior. It simply is doing what it's doing outside of the model and bringing its results to the model. So those are called exogenous variables. The ones that are being measured within the model are called endogenous. They're in the model, okay? So she even went on and hypothesized that what the sign would be on these relationships. So in other words, a positive means that higher peer support should lead to higher self-esteem. So it's that positive correlation. A negative one would be that a lower sense of control, in other words, a higher sense that someone else is controlling me externally, would lead to a lower sense of personal accomplishment. Okay? That was how she hypothesized it. Hypotheses are really good, especially if you think you might have some biases that you could put into the system. Write your hypotheses down before you go and see how many of them you're debunking.
So when she got done, she got these results. She had her hypothesized model. She did a whole bunch of series of tests and revisions to it, and she got a series of statistics that were better. So I've added on this slide here the different criteria that she's outlined for interpreting some of these different statistics. The reason we have so many of them is that these are pretty complex systems, and the way that these goodness and fit indices work, they're based on different components of the model. Some of them have a lot to do with sample size. Some of them have a lot to do with normality. Some of them are based on residuals. And putting them together, by themselves, none of them are particularly strong. Putting them with all the others, you get a mosaic of what's really happening in this model the way that we've set it up. And so in this case, we've got a really strong fit here. She's met the criteria for excellent fit. She's done a lot of changes here to get from the hypothesized to the final model. And here's sort of how it broke down from her hypothesis. She had originally had a line going from classroom climate to emotional exhaustion, and that one got eliminated during the process. And then these two bold black lines were not in her hypothesized model, but they got added to it. Okay? So you can really come up with some pretty robust, complex systems here and thinking about how does something lead to something else. Okay. So to kind of wrap some of this up, yes?
Can you take the question?
Sure, go ahead.
So on that particular model, were there any weights and variables involved?
Actually, all of the variables that you're looking at here, they're in ovals purposefully because all of them are latent variables. So actually showing the full model of this, there would have been about 5 rectangles attached to each one of these, that each one of them had their own set of observed variables. I didn't show any of those or their error terms in this model just to simplify it down a little bit. That was a great question. So you have to kind of think when you're presenting these sometimes, different audiences require different things, and sometimes you need those observed variables there to explain, especially if you're doing a confirmatory factor analysis. It doesn't make sense to not think about the observed variables. But in this case, where the real work was going on was inside of the latent factors. So I didn't bother with any of that for this. But I think there ended up being like 50 or 60 variables total that actually were on there. And you can kind of imagine adding that to this would make this a much messier piece to look at. So, good question. Okay, so this was a study that I did. In some ways, the line is very strong and ongoing because we're still thinking about the next piece after this. In mathematics, misconceptions are typically classified by the content area. So if I'm in an algebra class, then we think about algebra misconceptions. If I'm thinking about geometry, we think about geometry misconceptions. And that's been the way it's been for 30, 40 years. And most of the time when people studied misconceptions, they thought about the mistakes that students made. A lot of times there is a tendency to conflate errors with misconceptions. And there's been more awareness recently that there is a distinction that not all errors are based on deep misconceptions. And so a lot of research in the last 15, 20 years has really started thinking about, well, what are the misconceptions that lead to particular errors? And in my study, we were asking another question. What were the things that led to the misconceptions that would lead to the error? So we were trying to drill down a layer deeper. And the first step to that was really thinking about the way that content classifications would really work. So does it really make sense to classify these misconceptions by their content area? Does that help us? There's a quote from a long time ago that all models are wrong, but some models are useful. So we're not really asking whether the question is it right or wrong to do that? They are misconceptions, and they do emerge in algebra, so it's not wrong to call them algebra misconceptions, but does it help us understand something that we could use in teaching? Based on the literature, there were 6 different relationships that we needed to test. There were some studies that talked about rational number misconceptions,
as leading to probability misconceptions, in other words, causing problems for probability, both of which would then cause problems for algebra and geometry. There were other studies that reversed probability in rational numbers. So in other words, B is exactly like A, except these two ovals got flipped. Okay? Other studies really talked about them as if probability and rational numbers sort of acted equally. They covaried. And then other studies really talked about just one or the other of them being the predictor of all the others, the foundational misconceptions, if you will. That's the 5, and then the 6th one is saying they're all misconceptions and they're all related, and there's really not a causal structure going on here. All of these are latent factors. We used a 17-item instrument from a standardized tool, the National Assessment of Education Progress, NAEP. They have released items. They're rigorously developed and tested before they're ever used, and then they're released after they've been used for years. And so we use those items for each of these. So there are 3 items for geometry misconceptions and 4 for rational number and 5 for probability algebra. So there's a lot of rectangles not showing on this diagram because right now the focus of what we're talking about is on the relationships with the latent factors. Okay? What I found. First off, I took my sample, and to avoid the idea of overfitting my model to a sample, in other words, preserving some integrity to the generalizability of my study, I split the sample into 2 sets of data. I had the sample size to do that. So instead of doing 1 set of analyses with 1,300 students, I did 2 analyses with about 550 to 600 students. Okay? That's what this validation model is after I get my final model, I go run it on the other data set and see how good it is on the other data set. So now I've got a really strong case that I've got something that should be generalizable to the population. Okay? Well, you've got the result, the fit indices criteria from the previous slide on your handout. And if you notice, CFI on all 6 of them is above that 0.95 threshold. The RMSEA is below the 0.05 threshold. The SRMR is below the 0.10 threshold. And really their ECVI values aren't that different. A little bit of fluctuation in the chi-squared, but they're not nested models, so I can't directly compare their chi-squareds. I can use them when I'm thinking about the best fitting version of A3, but that's about it. What we really saw here was it didn't really seem to matter how we set these things up. They all fit really well, which is one of the reasons that 5 years later we're going, oh my goodness, after 3 more analyses, we almost think we understand what this means. But what we really did walk away with initially, very quickly, was if these all fit equally well, then it didn't really matter. We have ambiguous temporal precedence. We can't claim causality. So when I go back here, Model A does not make sense given the results. Even though Model A fits really well, it didn't fit any better than Model F did. And Model F is a much simpler model. Same thing for B, same thing for C, same thing for D, same thing for E. In other words, I would really need to have some strong evidence that says this is the model to go with. Now, what we found as we were doing our literature review was that there were these structures that kept popping up within each of these different factors. And they seem to sort of intertwine through all of them. So we then in our follow-up study asked the question, is there another classification system besides content area that would better describe what we're seeing? And so that's a follow-up analysis. And the answer to the question, just as a spoiler, was, as it turned out, the other factor set was stronger and had better discriminant validity among its factors, and it improved our fit of everything noticeably, okay? I didn't throw that one up here because we're really focusing on causal structures right now. That model was a comparison of 2 frameworks. not so much looking at causality within the factors of the other classification system. Here was where we were really focusing on the causality, and what we really ended up finding was that we don't have causality. Okay? It is really not true to say that rational number misconceptions will automatically lead to probability misconceptions. It is true to say that if we have rational number misconceptions, then to the extent that they intersect with a particular problem in probability or geometry or algebra, they could lead to misconceptions there too. Okay? So we have an association. And I just talked about that. Okay. So with that, I want to kind of wrap up today. I know that I did a little bit less with some of the deep statistics here, but I think that for this type of a setup, that might be more useful for having you something that you can actually take away with you that would be useful to your research. I hope that you find that helpful. If you actually find yourself that you're ready to do something like structural equation modeling, you should please contact me or have your advisor contact me. And so we can talk about maybe getting some support set up, because I actually will sometimes run a study group so that people can get like a 15-week course on just structural equation modeling and looking at different applications and the way to do it. And so if I've got people that want to do that, then that would be a good indication I need to set something like that up again. Our next seminar session is going to be on Wednesday, April 1st. I believe it's in this room again.
Yes.
And it'll be from 1 to 2:15. We're going to be looking at latent mean differences. And so we're going to be stepping back from causality, and we're going to be looking back at group differences again, but we're going to be thinking about, instead of comparing, I've got two variables, and I say, what's their correlation, and are there differences in their means? I'm going to say those variables are represented by a set of factors, and those factors we can estimate their means for, latent means. And are those latent means different? Which is a whole different level. And we're going to talk about why you might want to do that versus an ANOVA, and what are some of the benefits of using a structural equation modeling framework for that. So, if you have any questions, do we have time for questions? I'm kind of. Oh, we got 2 minutes. Wow.
Yes.
It's just my innate sense of time. That's what it is. Questions, comments, concerns, thoughts? Yes.
How are the values of latent variables?
That's a great question. To follow up the answer that I'm getting ready to give you, if you go back to my website that I think is on the handouts, back to session 1 and/or 3, there's some illustrations of what I'm about to describe. Basically, we say, okay, so here is how I set up these factors. I set up these factors in a particular relationship, which means that I'm actually going to measure a coefficient between these two things, okay? I have a set of observed data. And I say, okay, so first off, those data fall into these structures. And if I set up the observed data and then I compare it to what I would expect to get if my model held true, then I've got an estimated set of matrix estimates, and I've got an observed set of matrix measures. How different are they? So we look at, it's true that we actually do look at the matrix level first, and we say, how much variance is left over in the model if I use my model estimates to explain the observed data? Very much like we do with linear regression, where we say, okay, so we want to minimize the amount of variance that's left over between X and Y. We're trying to minimize that regression, the squared variances. Same thing here. It's not a squared variance anymore. It's actually a bit more complicated than that. But we're looking at minimizing what's unexplained between the observed and the estimate. And so the idea that I ought to be able, that I could take two causal structures and flip them and not have any difference, that's nuts. That's like saying it doesn't matter whether the egg hatched first or if I cooked it first. I'll get the same egg sandwich. It's like, well, no, that doesn't even make any sense. But that's how you do it. Is there's actually they set up an estimate of the model based on what we would expect given what we set up, and we look at what it looks like for real in the sample, and we see how different they are. Good question. Other questions? Yes.
Back to that same slide.
Okay.
If you've got multiple models, all with fairly equivalent fit to the observed data, is there any kind of metric like an AIC or a BIC to factor in the simplicity of the model?
Yes, actually, ECVI is an average. It's a per subject estimate of AIC. AIC is a measure of overall model variance. So I could have put AIC or ECVI up here. Unless the sample sizes are different on different models, there should be pretty similar in trends. But when we're thinking about model simplicity, every time we add a parameter, this value should get smaller. The best model, the most parsimonious model, ECVI should actually be going down. So for example, down here, one of the big reasons we didn't go with F3 instead of F2 is because all of the stats were exactly the same until we got to ECVI, and it actually increased instead of stayed the same. So in a lot of these, we saw they didn't change any at all. In that case, we're like, well, we need to make a decision about how theoretically viable that parameter is. But in this case, it actually increased, and we said, so at that point then, we're in high danger of overfitting to our sample, which will reduce our ability to generalize to a population. So yes, there are measures that build in penalties for being overly complex. Another way of thinking about that is that if you have a multiple regression model, all you have to do to get a better R-squared is keep adding x's, right? Because it's pretty dependent. I mean, you can just keep adding things until all variance is filled up. Doesn't mean that those variables are meaningful. What these measures do is penalize you for doing something like that. Okay. All right, I think that pretty much puts us out of time for today. Thank you all so much for being here and for being such attentive listeners. If you have questions, if you're one of the people watching over the web, please feel free to email me questions. It's just my last name, Rakes, @umbc.edu. Same goes for anybody that's in here, and I'll be up here for a few minutes if anybody has questions afterward. Thank you so much.